So hello, today I'm going to present my work entitled Multivariable Fractional System Identification, which is the collaboration between the MS laboratory with the University of Bordeaux and the Max laboratory, which at Link, donc, in Tunisia. So I'm going to start with the outline. First, I'm going to present the problem formulation. Second, we have two methods for meso-fractional system identification. First, I'm going to talk about two-stage algorithm. Then we have the output error method. Then we have the simulation examples. And we will finish with the conclusion and some prospects. So begin with the problem formulation here. We're going to consider a meso-fractional system, which represented by this figure. We have k input and single output. So our system is meso, multiple input, single output. Donc, the meso-fractional system is represented by this set of questions. We can see here the number of the input is k. Gk represents the fractional transfer function, and output is corrupted by an additive white noise. We can see here the fractional transfer function Gk, which is represented by this equation. We can see here also that beta G and alpha E K are represent the differentiation orders. So here I'm gonna talk about a new definition, which is the structured commensurability. In the case where the fractional transfer function is S commensurable, we have two cases. So if we have a fractional global S commensurate order, we can see here that for all subsystems we have the same commensurate order. And the second case, we have a local S commensurate order. In this case, we have S commensurate order for each subsystem. So here the parameter vector theta is defined as follow. You can see here, where rho gather all the coefficients of the meso transfer functions, and rho gather all the meso transfer function differential order. So here I'm going to define three cases in this for mu. So first case where we're going to search for a global S commensurate order, so mu equal to nu. In the case we're gonna search for a local S commensurate order for each subsystem, and the third case where our model is non-commensurate and root gather all the differential orders. Our objective here is to estimate the parameter vector theta of the meso model system. Unfortunately, we have two major problems in our work. So the huge number of parameters, so the dimension of theta is huge, twice more than an integer systems. And our model's orders are varied in a wide range at each iteration. So how to limit the number of parameters? We have implemented an initialization of differentiation orders. So here we're gonna start with the global S commensurate order. Once we estimate this, we're gonna estimate an S commensurate order for each subsystem, so local S commensurate order. And at the end, we're gonna relax the constraint of the commensurability, and we will estimate all the differential orders. Here, I'm going to present the two methods of the meso-fractional system identification. We're going to start with two-stage algorithm. We can see here that the two-stage algorithm basically is two-stage. First is the optimal and similar variable methods for coefficient estimation, and we will combine it with the Gauss-Newton algorithm to estimate the differential orders. Here I'm gonna begin with the optimal variable, optimal asymmetric variable for coefficient estimation for the CISO case. So for a CISO model, we have the error equation based to our figure here, where rho take this form, where phi take this form, and rho gather all the coefficient. So the approximation of last square estimate take this form. Unfortunately, here we have two limitations: the computation of time domain derivative of the input and the output signal. Second, the amplification of noise in high frequency. Hence, we try to derive the input and the output signals with the Poisson's filters. Unfortunately, here also we have a limitation. The estimation are based in presence of output noise. So Young has here Young has implemented an assignable variable estimator that take this form, that respects the long constraint, which we can see here. Young also showed that the optimal EV estimator is obtained for this form of filter that give unbased estimation and minimum variance. However, the denominator are usually unknown, so we have implemented an iterative algorithm to estimate A at each step, and we're gonna estimate the assignable variable here. I'm gonna talk a little bit about the historical of the optimal assignable variable. Here we can see that the first work was made by Young that deal with the discrete time system in the CISO case. Garnier also has attacked this work for the continuous time system also in the CISO case. And Victor has developed this work for the fractional system in the CISO case also. Garnier also worked on the meso system on the continuous time system integer. So our work here is to develop this work to the fractional meso system. Here in this case, the error function take the following form. The main idea here is to isolate the output of the kth subsystem and apply the CISO algorithm of the EV estimator. Here I'm going to summarize the algorithm. We're going to implement an iterative algorithm to optimize the ensemble. So here we can see that we're going to start with initialization the parameter vector row. And we have two loops. The first, we're going to take from iter1 to converge. And second loop is for each subsystem, we're going to implement the EV estimator. So we're going to generate the ensemble variable using the filter. We're going to update the filter with the first row we have. So with this filter, we're going to evaluate the pre-filter derivative of input and output data. Using this pre-filter data, we're going to compute the new estimate, and that's it.
And so on.
So here's here a diagram that resume the steps taken for the EV algorithm. So beginning with generating the assignable variable here from our auxiliary model, and isolate our output xk here. We're gonna use not our filter to derivative this data, and using this data we're gonna implement it in the refined IV algorithm to estimate a row. Here we're gonna pass to the Gauss-Newton algorithm. Here I'm gonna apply just a classical Gauss-Newton, which minimize the L2 norm. Here we can see the output error defined as follow, and the estimated output in this form. The Gauss-Newton algorithm is based on this equation, where the gradient is defined like this, and H is the approximated issue. Here I'm going to talk about the error sensitivity function. We're going to use it to calculate H, the approximation of Etienne. We have three cases in this time. If we have a global exponential order, so we're going to derive our error above with the nu. So here is the equation to calculate this sensitive function. The problem here is to implement the ln of P in MATLAB, which is impossible in our case. So we had search for a numerical solution. We use it to calculate the ACM. Here I'm gonna resume the two-stage algorithm. We can see here that we're gonna begin with the initialization, the parameter vector theta. Step 2 is to iterative all parameter estimation. So we're gonna do we're gonna compute the coefficient vector rho with the meso SRVCF that we are talking about. Second, we are gonna implement the Gauss-Newton algorithm, which is based on these steps. And once we have rho and the mu, we're gonna formulate the new estimate parameter, which is used to do the test if we're gonna break the loop or not, that converge or not. So here I'm gonna talk about the output error method. So the estimation problem is formulated as a minimization of problem of L2 norm. Here we can see our problem here. The output error is defined as follow, and the estimated output is defined as follow. So here I'm gonna resume the steps followed to estimate our theta. We're gonna begin with the initialization, the parameter vector theta. And the second, we're gonna iterate to converge the iterative Levenberg market algorithm for all parameter estimation. So we can see here our gradient and the pseudo Hessian and the market parameter. So the error sensitive function is represented by this equation, where the coefficient error sensitive function are calculated as follow, and the differential order error sensitive function are computed numerically. Here I'm gonna pass now to the simulation examples. So we're gonna begin with the first example, where we're gonna estimate the coefficient with the known differential orders. So the hypothesis here is the model structure are known, and the output signal is corrected by white noise, and the differential order are known. We're gonna compare between the meso SRVCF methods and the meso OO methods. We're gonna estimate the unknown coefficient. We'll performance analysis with the Monte Carlo for 75 runs, and we're gonna study the influence of the commensurate order in the end. So here we can see the table that illustrates the numerical result of a Monte Carlo simulation. We can see here that the rho estimated for each coefficient is close to the true parameter with the minimum variance. So here what we do is we had plotted the cost function that is represented by this equation versus the commensurate order for the
Abir, we don't hear you anymore.
And now? Hello?
No, yes, yeah, we hear you.
Okay, so here we're gonna plot the cost function versus the commensurate order in the range of stability of 0.4 and 1.35. So we can see here that our figure is smooth, and we can see that we find the minimum value of the creation equal to minus 19 dB. Note that the noise ratio, noise signal ratio equal to 120 dB, and we can see here that the modeling error is around 1 dB. The smoothness of the cost function allows us to implement the gradient-based optimization algorithms to estimate all the differential order in the second step. So the second example here, we're gonna estimate the coefficient with the differential order estimation. So here, our model structure are known, and the output signal is corrupted by a white noise, and the S-commensurate order are unknown. So we're gonna do a comparison between the MISO OSRVCF methods and the MISO OO methods. Here we can see the two examples that we use it. Here we can see at the left the S-commensurate order estimation with the MISO OSRVCF method, and on right we can see the S-commensurate order estimation with the MISO OO methods. We can see that both. We can see here that we estimate for beginning an S-commensurable global, an order S-commensurable global, which is in the two cases 10 to the 0.75, which is coherent with what we found with the cost function. And with this initialization, we will gonna relax the constraint of S-commensurability global, and we're gonna estimate three local S-commensurate order. We can see that we had converged to the true parameter for the two methods. You can see here, but the main difference between the two methods is the number of iteration. We can see here that the MISO methods converge faster than the MISO OSRVCF methods. So here I'm going to explain a little bit about the differentiation, the different iteration to converge. We can see here that both methods use the classic Gauss-Newton algorithm. Here in the OSRVCF method, we're going to use it to estimate just the orders, so the demands of H equal to 3. And in the case we are going to use it for the OO methods, we're going to use it to estimate all the parameters. This means that the dimension of H equal to 9. In the OSRVCF algorithm, the Hessian matrix contain only differentiation order sensitive function, and the MISO algorithm contain the coefficient sensitive function with the differentiation order sensitive function, plus the cross sensitivity function between the coefficient and differentiation order. So we can see here that the lack of information make the MISO OSRVCF algorithm slower to converge. And we can see here the table that illustrates the numerical result of a Monte Carlo simulation. We can see here that we had converged to the true parameter for the both methods. And we can see here also that the variance is minimal. So here we're going to relax the constraint of S-commensurability. We're going to estimate the differential order. We can see here in F1, we have an order of 2.8 and an order of 1.2. We can see here that our transfer function is not S-commensurability, and the differential order are not successive multiple of 1.2. This is why our transfer function is not S-commensurable. So same for F2 and F3. Here our model structure are known, and the output signal is corrupted by white noise, and differential order are unknown. So we're gonna present a comparison between the two methods, and we're gonna estimate the unknown coefficient with the differential orders. Here we can see that for both methods, we're gonna estimate a global commensurate order, which is converge to the same value for the two methods. Then we're gonna estimate three local S-commensurate order for both methods. And with this initialization, we're going to use it to estimate all the differential order. And we can see that for both methods, we had converged to the true parameter. You can see also the same thing for this method. The main difference between the two methods are the number of iteration, and we can see that the meso methods converge more faster than the other methods. Here the table that illustrates the numerical result of Monte Carlo simulation. You can see here that both methods converge to the true parameter with the minimal variance for the both methods. So finishing with the conclusion and some prospects. So here we can see that the optimal methods were used to estimate the coefficient that was combined with the differential order with the Gauss-Newton algorithm to estimate the differential order estimation. We had also developed an output error method for mesofractional system, and the main of the strong point in our work that we had developed an initialization process that was in three stages to estimate to converge better to the differential order and to reduce the number of parameters. The comparison between both algorithms give that the two methods give the same results, but the difference only in the time of converge. So the meso method converge more faster. In the scope of my work of the thesis is to apply this algorithm to modulate the climate system. And this is all. Thank you for your interest.
Thank you, Abir, for your presentation. So we have no back time for questions, so that's nice. So any question for Abir? If not, I will start. Can you remind me what is the noise that you put on your output data? So because I missed it somehow.
20 dB.
So it's just yeah, okay. So an output error.
But for the all differentiation order estimation was 150 dB. The third example here.
Yeah, but you put white noise just at the output, huh? So that's it. So effectively, so I have a question. Oh, no, because you showed that that it converges to the right parameter, but if you looked at the variance, I think yes, of the two methods, maybe methods on Monte Carlo simulation. And so what did we see there is that the variance is, yeah, that's the, why is the variance larger when you identify the system in the right model structure? I guess because when you do this IV method, so you make some normally the variance is maybe larger. Or maybe not. I don't remember well. Maybe Marion can tell me that. But so how can you explain that the variance seems larger with the output error while it's really the correct model structure?
Can you repeat the question, please?
So it looks like that with the output error, the variance of your identified parameter seems larger than with the IV method. While here the output error is just the correct model structure. So normally the variance should be smaller, well, the smallest possible, because you didn't find the full order model structure. So you have the prediction error identification is just the maximum likelihood. So the variance is the smallest. So why how you could explain those difference of the fact that the variance is slightly larger?
They are slightly larger.
Xavier, this is just a matter of a convergence test. As you know, these are iterative algorithms. So, I mean, it depends on criterion, on convergence criterion that was implemented. So one of the algorithms stops before the other. This is the only explanation. I mean, those variances are not very far one from another, but you are right. We are supposed to get exactly the true parameters.
I know when n goes to infinity, yes, but here the iteration, it's just sort of a gradient-based optimization. So so yeah, maybe you get maybe stuck somewhere because of.
I mean, here in this slide, number 19, there is a convergence test at the end.
Yeah.
So once you reach that convergence test, I mean, the algorithm stops. So I mean, there is a slight difference between both algorithms because of the stopping, because of this final test. That's it.
Okay. Yes, I understand. Yeah. It's always tricky with this nonlinear optimization. Okay, other questions? No? So then, if not, well, then I guess we are also very close to our coffee break. So I guess we'll do it now. So we'll have 30 minutes coffee break, half an hour. So we'll resume the presentation at 4:15. And then in the end of this afternoon, we'll have two presentations, one by Vincent Laurin and one by Kevin Collin. So, well, have a nice coffee break and see you in half an hour then. Bye-bye.